Okay, nice. Thanks to the organizers and thanks for the interesting talk so far. As Eduardo said, this is slightly changing gears and it's not a notebook. So I'm going to talk about dEFT, which stands for Differential Effective Field Theory Tool. So what is dEFT? Well, it's a Python tool, obviously, and it aims to do one thing well, which is constrain the parameters of standard model effective field theory using differential cross-section measurements as input. So the dEFT design goals is exactly that, to be simple, to be easy, and to be someday extensible. In a word, it's trying to be dEFT. And it's very much a work in progress. So it's in an alpha state just about. It's living on GitHub right now and can be snooped at the link there. We're definitely not ready to have something really publicly consumable, but we're pretty close to it. And with a little know-how, you can make dEFT work as you might like. And we do have a plan for a stable documented release, I hope within 6 months and maybe within 1 year. Okay, so what does dEFT do? Bird's eye view. So to do a constraint analysis on the SMEFT, you have two basic ingredients. You need the SMEFT itself. You need a theory predictions for an observable that you might hope to measure. So the example here on the top left is the differential cross-section as a function of MTT bar, so the invariant mass of a top quark pair. And you see a bunch of histograms here which represent the predictions of the SMEFT for various values of the free parameters of the SMEFT, which are usually denoted C, otherwise known as the Wilson coefficients. And they're the free parameters of the theory. We won't get into the physics of it, but they're there and define what the theory says. Of course, we also have measurements of those same observables nowadays. We have many, and they're getting more and more precise. I show an example from CMS from a couple of years ago of MTT bar. So they are the two crucial ingredients that come together in order to constrain the SMEFT, and that's where dEFT comes in. First of all, it builds a regression morphing model. That's the name I give it. But really, it's a simple thing. It's just a parametric model of that differential cross-section, so that histogram, or otherwise you could think of it as a vector, as a function of those free parameters. And it builds this parametric model from an array of theory predictions. And then the second crucial ingredient, of course, is the data. And together, dEFT produces a posterior probability density function as a function of those parameters, those coefficients. And if you have n coefficients under consideration, then you have an n-dimensional posterior function. And of course, we'd like to marginalize that. And dEFT also does that, utilizing some packages that I will talk about presently. Okay, so to brush a lot of interesting physics under the carpet for the purposes of this talk, we can say that cross-sections in general in the SMEFT are nothing more than multivariate polynomials. So they have a constant term, which is the standard model cross-section. And then you have a bunch of linear and quadratic terms, which represent the new physics terms and the contributions that the SMEFT describes. You have a list of contributions that depend linearly on these coefficients, and a set that depend on the products of all pairs of coefficients, including the squares of each coefficient. So you have a bunch of unknowns here because all the linear terms have slopes, which are called beta I here, and you have additional unknowns, which are the coefficients of the quadratic contributions beta ij. So if you could determine the unknowns here, you could work out the SMEFT prediction at any point in the parameter space of the SMEFT. But these unknowns are dependent on the observable you're after and the actual theory calculation you have in hand, for instance, the order of QCD. So what dEFT does is the simplest possible thing you could imagine to determine those unknowns. It simply minimizes the sum of squared differences between the predictions, the theory predictions that you might pull out of these days, most likely MadGraph and some SMEFT model, and a bunch of predictions of your parametric model. And so if you sum across all bins and all predictions, you get this squared sum, which of course should be minimal if you have the correct values for the unknowns. And that's what dEFT does, typically over a large number of predictions, which are typically much larger than the number of unknowns. And we do this because typically a Monte Carlo prediction will have some uncertainty. And if you over-constrain this system, you become less susceptible to excursions in the model from Monte Carlo statistical uncertainties. Of course, you can test how well your model is doing by just comparing to independent theory predictions at independent points in the parameter space. Okay, so once you have your parametric morphing model of your differential cross-section, dEFT then just employs two fairly well-known and popular Python packages to do the rest. First of all, emcee comes in, and what emcee does is explores the parameter space intelligently. And at each point, it uses dEFT to produce a differential cross-section prediction, compare it to data, and produce a log likelihood. And that's what you see in the GIF here. You have the exploration of the parameter space, in this case, just 2D for visualization purposes. You have the changing morphing prediction, differential cross-section, matching well and not so well with the fixed data, and then the log likelihood varying accordingly. And then another well-known package, Corner, takes that resultant in-dimensional log likelihood, posterior, and marginalizes it into nice visualizable one-dimensional and two-dimensional PDFs. And from there, it produces Bayesian credible intervals, which are your ultimate statement about the content of your data. On the purely practical side, I hinted that dEFT one day should be extensible and as modular as possible. So an entire analysis is defined in a single readable JSON file, which consists of two main blocks. First of all, you define your data, the bins in which your data lives, the central values, and usually you need a covariance matrix for differential cross-section, as you have interbin correlations due to the unfolding process. That should all be encoded there. Happily, these days, this information is available on HEP data, so can be easily integrated into dEFT. And secondly, you just need the inputs from which the model is built. So that consists of a long list of theory predictions, points in coefficient space to which they correspond. So with those two together, the rest is automated. Here I show an example dEFT analysis that has just arrived on the archive as of yesterday. And it's just the example I've been using to demonstrate the capabilities of dEFT so far. And you see it's the impact of the TWZ process being measured at the high-NUME LHC in the future as a demo. Okay, so to summarize, dEFT aims to do one thing well, which is measure or derive constraints on SMEFT parameters from differential cross-sections. It does this by forming a regression morphing model of the differential cross-section under consideration, and then from there on out utilizes emcee to estimate the posterior PDF by exploring parameter space and marginalizing that to produce final credible intervals. It's in an alpha state, but it's progressing quite nicely, most evidenced by the first analysis using dEFT appearing in the archive, and is available on GitHub right now. And we do hope to have something stable, version 1 appearing within 6 months to a year. Okay, thank you.
Thanks so much. So you have a couple questions, 2 or 3 questions, if you want to share them, or I share them.
I see them on Slido.
Sorry, yeah.
I see them, yeah. So okay. I think Grant's question, is it really limited to differential cross-sections, for example, the differential TT-bar chart? Yeah, that's a very good question, and something that's very on the tip of my tongue as I'm working on a chart asymmetry analysis with exactly this question. So not in the medium term, it's certainly not limited. Just right now, I would, you know, it's just been designed to work with this multivariate polynomial. So it's just a matter of getting in the weeds and making sure that if we do it for something like a charge asymmetry, and that it would work out of the box. And I just wouldn't be sure of that until I see it with my own eyes. But the method would be very similar. And then an anonymous question says, how does dEFT compare to the traditional EFT method where the beta coefficients are thought to some interpolation of EFT Monte Carlo results? So what I can say is the morphing method that is described in an Atlas note from maybe 2014 gets the beta coefficients from an exact matrix solution. So it solves a matrix equation and gets an exact solution. So in spirit, that's very similar to what I'm doing here. Except if the input predictions carry some Monte Carlo statistical uncertainties, actually some parts of your matrix, your betas, can be quite poorly constrained. So if when you actually do your fit to data, those terms become important and are poorly constrained from your initial solution to the matrix equation, you can actually get big excursions in the predictions. And that's what actually prompted this idea of over-constraining the system by using lots and lots of theory predictions and suppressing the effects of Monte Carlo statistical uncertainties. I'm not exactly sure if that was what is being asked by interpolation, but in essence, what we're doing here is fitting the betas first before we fit to the data. Maybe that's clearer.